Alright, so today we're going to be talking about something called the average value, and then we're going to talk about the mean value um, theorem for definite integrals. So we already probably saw the mean value theorem for um, like derivatives, but this is a different one. So the average value is basically the mean value of a function, and so like intuitively this kind of means like it represents the uh like the mean value of the function on some interval, right? So if I had like an easy example is like if I had a linear function from a to like b, right, and this is 10, right, you can kind of say that like the average value of this function is 5 on this interval, right? Because this is a linear function, so it's like easy to reason about that, like um, half the time it spends above 5 and then half the time it spends below 5 on this interval to a to b. But how do we generalize this, especially um, for basically all functions, right? How do we generalize this? And it's kind of hard to think of because a function, like, this is a continuous function, right? So it takes on infinitely many values. But we kind of talked about how the integral of a function from a to b, right? So the integral of some function f of x dx from a to b is equal to the area under the curve of the function, right? And we kind of talked about how the area is a notion of um, kind of summing up infinitesimally small, like intervals that the function takes on, right? So if the function is something like this, we're like making these we're like estimating the function with these like small rectangles, and then we're shrinking the size of those rectangles to near zero. And then when the size of the rectangle is near zero, then each like interval essentially just becomes f of x, right? That it takes on. So you can kind of think about the area of the function as summing up all like the f of x values that it takes on, which is not actually what's like going on, but you can kind of think about that in that way. And then we know that like in general, we know that the sum or the average of any like set of discrete numbers, right? So let's say we have I numbers, right? Or let's say we have n numbers. So the average is just a sum of like all of those n numbers divided by um, n, right? So this is just like a compact way to represent average of n numbers. So we can kind of do the same thing with the integral. I kind of motivated how the integral is kind of summing up all the little values f of x takes on and combines it on an interval and combines it together, right? And so this and we went back to the Riemann sum, right? The Riemann sum had the summation in it, except the limit was of the intervals were going towards zero, right? So that's the summation portion. This integral represents the summation portion. Now we just need this averaging portion, right? And so what is the analogous version of n in this case, right? And if you were to think about it, n here would be the size of the interval, right? So if we were to if we're calculating the average or the sum from a to b, that means the size of the interval is simply 1 over, or the size of the interval is b minus a, right? And so to find the average value, we simply multiply by 1 over b minus a. And you see how this term that I've created here is very analogous to how you'd find the average in a set of discrete numbers, right? So what we've arrived at, 1 minus b minus a times the integral from a to b of f of x dx. This is the average of function f on a to b. And so that is how you'd find an average value of a continuous function. And so let's try to do an example. So example 1. F of x is equal to 4 minus x squared, and the interval we're worried about is from 0 to 3. Find the average value of f of x is equal to 4. So find average value, right? And so this is just applying our definition. So 4 minus x squared from 0 to 3 dx. And then we know that the integral of this is simply x cubed over 3 and then plus 4x. And then evaluating that from 0 to 3, we get minus 27 over 3 plus 12 minus 0. And so this is negative 9. Negative 9 plus 3 is simply 3. So that's the integral. And then the size of our interval is 3. So we have to multiply that by 1 over 3 minus 0, which is just 3. And so 1 is our average value. And so a follow-up question is, does 4 minus x squared, which is f of x, take on 1 on the interval? And so let's find that out, right? So 4 minus x squared, we have to find out where it's equal to 1. And that's simply x squared is equal to 3. And then we get that is x squared is equal to 3 when x is equal to plus or minus root 3. And the question asked is if it takes on it on this like interval between 0 and 3. And we know that root 3 is less than 3 and greater than 0. So the answer to that is yes. And so the reason the reason for the follow-up question is because this brings about the mean value theorem for definite integrals. And it has a very similar flavor for the mean value theorem that we learned before for derivatives, except this talks about integrals. And so this theorem states that if f is continuous on the interval a to b, closed interval, then at some point c on a to b, and then in this case it's a closed interval. If you recall the one for derivatives, it was an open interval. But then then at some point c on this interval a to b, f of c is equal to 1 minus b minus a times a f of x dx. So essentially, in other words, what we're saying is that for some point c on this interval between a to b, we have f of c is equal to the average value. And yeah, so I'm just saying that for a function, there will be some point where the value of the function is equal to the average value on that interval. And to try to motivate why this is true, right? Let's say we have a function that looks like this. This is A, this is B, right? And let's say that our average value of this function is at some point is some point like the average value for this is like y is equal to some value c. So like this is c over here. And so the area represented by that is like all of this shaded region, right? So the shaded region is simply f of c times b minus a, and that is equal to f of x times dx on a to b. So we're saying that this shaded region that I represented over here, with the height being f of c, is the same area as my entire curve, right? From a to b. And it makes sense that our f of like we must have a c inside of this like in between the a to b interval for this to be true, because we will have like above the value of c, right? If we were to draw a rectangle to estimate the total area, it will be an overestimate, and below like this pivot point that we chose of c, right, we'll have an underestimate of the area. um and so, because of the way averages work, you always have areas greater than, and you always have areas less than. And so, it must imply that there's like some point c in the interval between a to b where f of c represents the average value. In other words, if we were to multiply the value of f of c times like by the size of the interval, we would get the area of the entire curve on the overall interval. And I understand that this is kind of hand wavy, but this is like the best sort of intuition and proof I can give to you. If it doesn't make too much sense, it's fine. If anything you would take away from this, it's this fact of the mean value theorem. And yeah, that's basically it.